You know that feeling, that pit in your stomach when a project deadline is just looming?
Mhm.
And it feels less like a clear finish line and more like, well, just a foggy guess. Or even worse, when the timeline you thought you had just completely unravels.
Oh, yeah. That uncertainty is, I think, one of the biggest stressors in any project, big or small. If you don't have a clear schedule, you're basically navigating blind.
Absolutely. But okay, flip that feeling. Imagine having a roadmap, right? Knowing the steps, understanding the time involved, and feeling, confident about hitting your targets.
That's the power we're talking about today.
Exactly. We're doing a deep dive into plan and manage schedule.
And we're pulling this straight from source material that's really designed to map out these core concepts.
Hmm.
It's specifically Task O3 within the process domain O2 of the new PMP exam content outline.
Right.
So this stuff isn't just, foundational for exams. It's absolutely crucial for real-world project success.
And what's interesting, our source material really emphasizes that scheduling isn't just one size fits all anymore. It covers both the, let's say, traditional predictive ways of building a schedule.
Right, the waterfall approach.
And also the more dynamic, adaptive approaches you see in agile or hybrid settings. It even points out that the exam itself reflects this mix.
Yeah, that's key. The core principles like identifying work, understanding dependencies they apply across the board,
Yeah.
but how you actually plan and control that timeline. That can change quite a bit depending on your methodology.
Okay, so let's dig into this. Our mission here really is to walk you through the essential steps and techniques that project managers and teams use to build, execute, and, crucially, keep the schedule on track. Whether it's, a super predictable construction project or maybe a fast-moving software release, we want to get to the core nuggets of why these steps matter and what actually makes them work.
And, the process often kicks off with planning how you're going to handle the schedule for the whole project.
Wait, planning. How you plan? That sounds a little recursive.
It does, doesn't it? But it's actually super important. This first step is called plan schedule management. Think of it like creating the rule book for how you'll create and control the schedule later.
A rule book.
Exactly. And the output here isn't the schedule itself, okay? It's the schedule management plan.
Gotcha. So what kind of rules are we talking about in this plan?
Well, it defines things like the methodology you'll use, maybe critical path, maybe an agile approach. It specifies the software tools you might use, the level of accuracy you're aiming for with estimates,
Okay.
even the units of measure, like are we talking hours, days, story points. Plus, it covers how you'll measure performance, maybe using earned value management and what the report should look like. It basically sets the stage for consistency.
Okay, that makes sense. It's the blueprint for creating the blueprint, sort of.
Mhm.
And the inputs would logically be things like the project charter, the overall project management plan, that high-level stuff.
Exactly right. That high-level context informs your detailed plan for actually managing the schedule itself. Once you have that rule book in place, then you can start breaking down the actual work.
Right. Which brings us to define activities. This is where you list out everything that needs to get done.
Precisely. You take those major deliverables or work packages from your work breakdown structure, the WBS, and you decompose them. You break them down into specific, actionable schedule activities.
Okay.
The key benefit here is that you're shifting from what you're building to the specific tasks you need to perform to build it. And these activities, importantly, they aren't actually shown on the WBS itself, but they are derived right from it.
Okay, so if the WBS says, like, build foundation, the activities might be excavate site, pour concrete, cure concrete, those really granular steps.
Exactly that. The sources point to decomposition as a primary technique here. And another really important one, especially when you don't have all the details up front, is rolling wave planning.
Rolling wave planning, is that about adding detail as you go along, like planning in waves?
Yes, exactly. It's a form of progressive elaboration. You plan the work that's coming up soon in high detail, but work that's further out. You plan that at a higher level.
Okay.
Then, as the project moves forward and you learn more, you break down that future work into more detail, usually just before you're actually ready to start it. It acknowledges that trying to perfectly detail everything on day one is often, well, impossible and frankly wasteful.
Yeah, that makes total sense, especially for projects where requirements might evolve or things are uncertain. So what are the main outputs from defining all these activities?
You get the activity list, that's every single activity identified. Then you get activity attributes. These are details about each activity, like dependencies, maybe resource needs, constraints, things like that. And finally, the milestone list.
Milestones, those are the big checkpoints, right?
Yes, the significant points or events in the project lifecycle. And crucially, they have zero duration. They represent the completion of something significant, or maybe a key decision point, not the work being done itself.
Got it. Zero duration, key events. Okay, activities listed, milestones identified. Now we need to figure out the order they happen in. Sequence activities.
This part is all about defining the logical relationships, the dependencies between all those activities you just listed. You can't paint the wall before you actually build the wall.
Seems obvious, but yeah, getting it right is vital. What's the main tool used for this sequencing?
It's called the precedence diagramming method, or PDM. That's how you visually map out those relationships, usually in a network diagram.
Okay, PDM. And the sources break down the different types of relationships you can have.
Yes, there are 4 main types shown. First is finish to start, FS. This means the successor activity, the one that comes after, can only start after the predecessor, the one before it finishes.
Right, that's the most common one, I guess. Like, finish the foundation before starting the frame. Exactly. Then there's finish to finish, FF. Here, the successor activity can only finish after the predecessor finishes. An example might be, electrical work must finish before the final plumbing inspection could be considered complete. Maybe they both need to be done for sign-off.
Okay, finish together.
Then start to start,
Yeah.
SS. The successor can only start after the predecessor starts. Think. Site preparation has to start before you can begin digging a trench. They might run in parallel for a while, but the second one can't kick off before the first one does.
Got it.
And the last one, start to finish, SF. This one's rare. The successor activity can only finish after the predecessor starts. The classic example is system migration. You cannot finish shutting down the old system until the new system has started operating. The start of the new enables the finish of the old.
Wow, okay. These examples really help clarify the differences. And dependencies aren't just about the type of link, but also why the link exists, right?
Exactly. You've got mandatory dependencies. These are legally required or maybe contractually obligated, or just inherent in the nature of the work, like the foundation example, physical limitations.
Sure.
Then you have discretionary dependencies. These are based on best practices or maybe just a team preference. Like maybe you prefer to finish all the plumbing before starting electrical just for ease of inspection, even if technically you could overlap them, sometimes called preferred logic.
And are they internal or external dependencies? Is that another factor?
Yes, good point. Internal dependencies are within the project team's control. Coding has to finish before testing can start. External dependencies are outside the team's control, like waiting for a government permit before you can begin construction.
Okay, so lots of ways activities can be linked up. What about leads and lags? What do they do?
Right, leads and lags modify those relationships. A lead allows a successor activity to start before its predecessor finishes. It's basically planned overlap.
Like starting the painting a couple days before the plastering is totally, completely dry.
Exactly. You're accelerating things. A lag, on the other hand, is a required delay after a predecessor finishes before the successor can start. That concrete curing for 7 days before you can build on top of it, that's a classic lag.
Okay, so leads pull things closer together in time, lags push them further apart?
Yes, essentially. Though it's worth noting, sometimes lags can be used to, let's say, pad the schedule or hide uncertainty if you just add buffer time because you're not quite sure how long a handoff will take. Good practice is to avoid that.
Makes sense. And the output of all this sequencing work is the project schedule network diagram, that visual map.
That's the one. It shows all the activities and how they're connected.
Great. Okay, activities listed, they're ordered, relationships defined. Now, the big question, how long will each one actually take? Time for estimate activity durations.
Right. This is the process where you figure out the number of work periods, days, weeks, hours needed for each activity, taking into account the resources you expect to use. The obvious benefit here is getting an expected duration for every single task.
Okay. The sources list several ways to estimate. What's the fastest way, maybe the least precise one?
That would be analogous estimation. It's quick because you're basically looking at historical data from a similar past activity or project. You say, hey, we built a feature kind of like this last year, took 5 days, so let's estimate 5 days for this one too. It's very top-down and really relies on how similar that past project actually was.
Okay, and a step up in accuracy from that.
Probably parametric estimation. This also uses historical data, but it combines it with statistical relationships or parameters. So if you know historically it takes, say, 2 hours per square foot to paint a certain type of wall, and the wall you need to paint is 100 square feet.
Then you estimate 200 hours.
Exactly. It's generally more accurate than analogous if your parameters are well-defined and the historical data is reliable for that specific context.
Gotcha. 3-point estimation. That sounds like it adds a bit more rigor to get a better guess.
It definitely does. It explicitly accounts for uncertainty, which usually makes it more accurate than just picking a single number. You get 3 estimates for each activity. An optimistic guess, O, the most likely scenario, M, and a pessimistic estimate, P.
O, M, and P.
Right. And the source material gives 2 common formulas to combine these. There's the triangular distribution, which is just a simple average, O plus M plus P.
Okay.
And then there's the beta distribution, often associated with P, which gives more weight to the most likely estimate, O plus 4M plus P6.
Weighting the middle more heavily. So for that example in the source, optimistic 14 days, most likely 27, pessimistic 49. If you use the simple triangular formula, 14 plus 27 plus 49 is 90. Divide by 3 gives you 30 days.
Exactly. It gives you not just a single number, but implicitly acknowledges the range and provides a statistically considered average. It helps reduce bias.
That seems much more realistic than just picking one number out of the air. What about the most accurate method, the gold standard?
That's generally considered bottom-up estimation. Here, you break the work down into the smallest possible pieces, estimate each tiny piece individually, and then roll those estimates up to get the total duration for the larger activity or work package.
So, super detailed.
Very detailed. It's highly accurate because it's so detailed, but the downside is it's also the most time-consuming and potentially costly way to estimate. You really need detailed information available to do it well.
Makes sense. And of course, you can always lean on expert judgment too, right?
Absolutely. Drawing on the knowledge and experience of people who are really familiar with a specific type of work being estimated is often a key input, sometimes used alongside these other techniques.
Okay, fantastic. So we've estimated durations for all the activities. Now, finally, we bring it all together and develop schedule. This is where the actual schedule comes out.
This is where the magic happens, yeah. You take that activity list, the sequences you define, the duration estimates, the resource requirements you've identified, any constraints, and you analyze it all together to build the actual project schedule model. The model.
Yeah, the model that generates the schedule. This is what you'll execute against, monitor progress against, and control changes against.
And this step uses that network diagram we talked about earlier, the PDM.
Yes, schedule network analysis is absolutely key here. And the star player in that analysis, especially in many predictive or traditional projects, is the critical path method, or CPM.
CPM, that sounds really important. What's the core insight it gives you?
CPM helps you figure out the minimum possible duration for the entire project. It does this by identifying the longest sequence of dependent activities through that network diagram we built. That longest path is the critical path.
Okay, the longest path.
And the critical part is this. If any activity on that critical path is delayed by even 1 day, the entire project's finish date is delayed by 1 day, unless you can recover that time later, of course.
So the critical path has basically zero slack or flexibility. Exactly. Our sources define total float, sometimes called total slack, as the amount of time an activity can be delayed without delaying the overall project completion date. Activities on the critical path have zero total float.
Okay.
They also mention free float, which is a bit more specific. That's the amount of time an activity can be delayed without delaying the early start of its immediate successor activity. Float, in general, tells you where you have scheduling flexibility off the critical path.
Right. And the sources show how you can actually trace the different paths through a network diagram, add up the durations, and find that longest one. That feels like a really crucial exercise.
Oh, it is. Understanding which activities are critical, which ones have zero float, is absolutely fundamental to managing the schedule effectively. Knowing where to focus your attention if things start to slip.
Makes sense. But schedules aren't just about time, right? What about the people and equipment needed? Resources.
Good point. You also need to factor in resources. That's where resource optimization comes in. Schedules are often initially developed assuming you have unlimited resources, which is rarely true, right?
This step adjusts the schedule based on the actual availability of key resources: people, equipment, facilities. There are 2 main techniques mentioned: resource leveling and resource smoothing.
Resource leveling. That sounds like trying to make the workload level, maybe balance the demand for resources over time.
That's a great way to think about it. Leveling adjusts activity start and finish dates specifically to address resource constraints or to smooth out peaks and valleys in resource demand. So if you have one specialist assigned to 3 different tasks that the initial schedule says should happen all at the same time.
Which they can't do.
Exactly. Leveling would likely push 1 or 2 of those tasks later so the specialist can work on them sequentially. The really important thing to remember about leveling is that it can change the critical path and potentially extend the project's overall duration.
Ah, okay. So you might accept a later project end date just to avoid needing, say, 5 engineers when you only have 3 available. Yes, precisely. It prioritizes keeping resource usage within limits, even if it pushes out the timeline. Resource smoothing, on the other hand, is a bit different. It tries to keep resource usage within predefined limits by adjusting activities only within their existing float.
Within their slack time.
Exactly. It does not change the critical path, and it does not change the project completion date. It just optimizes resource use within the flexibility you already have.
Ah, okay. So smoothing is like tweaking things within the existing wiggle room, while leveling might actually redraw the critical path and change the end date.
That's the core distinction, yes. Smoothing works within the schedule's boundaries. Leveling might change those boundaries to accommodate resources.
Got it. Now, what if the schedule you come up with, even after all this, just isn't fast enough? The deadline is sooner. Can you shorten it?
Yes, you can try, using techniques called schedule compression. The goal here is specifically to shorten the project duration without reducing the project scope.
Okay, same work, less time. How?
2 common techniques are mentioned: crashing and fast tracking.
Crashing. That sounds kind of intense. And probably expensive.
It often is. Crashing involves shortening the schedule duration by adding more resources to specific activities. Think paying for overtime, hiring extra contractors, maybe using faster but more expensive equipment.
Right.
A key point here is that you should really only crash activities that are on the critical path. Adding resources to activities that already have float won't shorten the overall project duration, it just costs more.
Good point. Focus the extra resources where they actually impact the end date. What about fast tracking?
Fast tracking involves taking activities or phases that were originally planned to be done sequentially one after the other and overlapping them, doing them in parallel instead.
Like maybe starting construction activities before all the detailed design drawings are 100% finalized.
That's a classic example, yes. The trade-off here, as the sources usually note, is increased risk. You might have rework later if the initial work was based on incomplete information from the phase you overlapped it with.
Okay, so schedule compression is really about making deliberate trade-offs, usually involving cost increase with crashing or risk increase with fast tracking to gain time on the schedule.
Exactly. It's never free.
Hmm.
Now, all this detailed sequential planning, critical path, baselining, this is very typical for predictive waterfall-style projects. But scheduling looks quite different in adaptive or agile environments, right?
Yeah, absolutely. How does Agile handle schedule management? It's not like they typically have a rigid 18-month Gantt chart locked down from day one, is it?
No, generally not. It's much more iterative and adaptive. In Agile, the team works really closely with the product owner to prioritize the work, usually held in a product backlog. They develop a higher-level roadmap that shows anticipated release functionality over time, maybe for the next, say, 3 to 6 months. But the detailed scheduling happens in much shorter cycles.
Time box scheduling, is that the term?
Yes, that's common. Often called iterations or sprints, typically lasting maybe 1 to 4 weeks. Or sometimes they might use a continuous flow model like Kanban, where work is pulled through stages as capacity allows, without fixed iterations.
Okay.
Either way, the team pulls a chunk of high-priority work from the backlog into an iteration, and they commit to completing that work within that fixed time box.
So how do they estimate and track progress in this kind of iterative model? It's not usually in hours or days for features, is it?
Often not, no. They frequently use relative estimation techniques, like story points, to estimate the effort or complexity of different pieces of work relative to each other. And a key metric they track is velocity.
Velocity, what's that measure?
Velocity is basically the amount of work often measured in those story points that the team consistently completes and gets accepted in a single iteration or sprint.
Ah, so velocity is like the team's measured throughput or capacity per sprint.
Yes, exactly. It becomes a really key metric for forecasting. Based on their historical velocity, the team can predict roughly how much work they can likely get done in future iterations, or estimate how many iterations a larger feature or a whole release might take. Agile release planning then focuses on defining the content for multiple upcoming releases, broken down into those shorter iterations with target dates.
Okay, so the planning horizon is different. It's less about locking down one fixed end date far in the future and more about planning a series of valuable increments and releases over time.
It really aligns well with that rolling wave concept we mentioned earlier, but applied continuously. The most detailed planning happens right before an iteration starts, and it focuses only on the work selected for that specific time box.
It's fundamentally built for responding to change and delivering value frequently.
That makes a lot of sense. Okay, so we've seen the whole planning cycle now, from deciding how to plan, breaking down the work, ordering it, estimating it, putting it all together into a schedule model with different flavors for predictive and agile. What happens after the schedule is built and approved?
Well, you can't just create it and forget it. You have to keep it on track. And that brings us to the control schedule process.
Right, monitoring progress and managing changes when things go off track.
Exactly that. It's all about tracking the actual project status against your schedule baseline. That's the approved version of the schedule you developed. And crucially, when things inevitably deviate from that baseline, you need processes for managing those changes effectively.
How is progress measured differently in, say, a traditional project versus an agile one, according to the sources?
In traditional projects, you're typically monitoring progress directly against that fixed schedule baseline. You might use methods like comparing actual start and finish dates to the planned dates, tracking milestones, or using metrics like earned value EV analysis to see if you're on track in terms of work accomplished versus planned.
Okay.
Any proposed changes to that baseline schedule usually have to go through a formal change control process for approval.
Right. And in agile, how does control look there?
It's more focused on empirical control based on observation. Progress is primarily measured by the amount of working software or valuable product delivered and accepted by the product owner. You see the completed features demonstrated in sprint reviews or similar events. Teams compare the work they actually completed against their initial estimates for the iteration. They track their velocity. The focus isn't so much on sticking rigidly to an old baseline, but on adapting the plan for future iterations based on the current reality, progress, and any feedback received. Retrospectives are also vital here for inspecting and adapting the process itself to improve future performance.
Okay, adapting the future plan rather than just tracking variance against the past plan. What tools help people visualize and understand schedule performance in either context?
Oh, there are lots mentioned. Gantt charts are the classic visual for showing tasks over time with their dependencies laid out. Milestone charts just highlight the key dates and events.
Sure.
Network diagrams are still useful, especially for visualizing that critical path and complex dependencies. And roadmaps give that higher-level strategic view, often used for outlining releases over quarters or months.
And for more visual workflow tracking, especially in Agile.
Yeah, things like task boards or Kanban boards are very common there. They provide a visual representation of the workflow like to do, in progress, done. And burn-down charts are frequently used to track the remaining work against time, showing if a team is on track to complete their committed work within a sprint or release. Velocity charts track that team capacity over time. And techniques like earned value and variance analysis can still be powerful, sometimes adapted for use in hybrid or larger agile projects to track overall performance against a release plan or budget.
Got it. It sounds like control schedule, regardless of method, is really about constant vigilance, measurement, and communication, keeping your finger on the pulse.
It absolutely is. A schedule isn't static. It's a living document, or at least a living plan. Tracking progress, analyzing any variances that pop up, forecasting future performance based on trends, and managing changes effectively. These are all essential activities for project success.
Wow. Okay, we've really covered a lot of ground there. We've gone from that initial thinking about how to plan the schedule all the way through defining the work, ordering it, estimating, building the model, and then keeping things under control once work starts, looking at both the traditional and the agile ways of thinking.
Yeah, and it's clear there's a real structured way to approach project timelines, even with the differences.
Yeah.
Whether you're meticulously decomposing a WBS in a predictive world, or you're pulling user stories into a sprint in an agile one, that fundamental need to identify the work is still there.
Right.
Sequencing dependencies is crucial. Whether you're building a complex network diagram, or maybe just mapping out the basic flow of features on a Kanban board. And estimating duration, even if it's relative estimation using story points, is still necessary for any kind of forecasting or planning.
And understanding these core concepts we talked about, like the critical path, resource constraints, schedule compression techniques, it gives you real insight into why projects often face the challenges they do and the kind of trade-offs project managers are constantly making.
Exactly.
Just knowing the difference between resource leveling and resource smoothing, or between crashing and fast tracking, helps you decode those project conversations and understand the decisions being made.
And I think for anyone listening who works in or manages projects, or even just works on projects, understanding these principles, whether they lean predictive or agile,
just makes you more effective at planning your own work, collaborating with the team, and communicating realistically about timelines and potential hurdles.
It really drives home that schedule management isn't just about, drawing some lines on a calendar. It's a really dynamic process of defining, ordering, estimating, analyzing, and then constantly monitoring and adapting the work as it progresses.
And it was interesting how, even with all the detailed planning and emphasis on baselines in the traditional methods, the sources also consistently brought up techniques like rolling wave planning and, of course, the whole adaptive nature of agile scheduling, acknowledging uncertainty.
Yeah, that focus on adaptation, it leaves us with an interesting thought, doesn't it? We've mapped out how to meticulously build and control a schedule, but given that projects, let's be honest, rarely unfold exactly as planned down to the last detail, maybe the ultimate value in schedule management is less about creating that single, perfect initial plan and more about the ongoing process itself, the process of planning, monitoring, learning, and adapting along the way.
Something to definitely think about as you tackle your next project or initiative.